On number 7, we have to use the Wronskian to show that a function and x times a function for any positive function will always be linearly independent. And so remember, the Wronskian looks like this. I'm just going to put them in as f and xf. You can leave off the f of x part. Anyway, the Wronskian is going to look like this. Remember, you put your functions and then you take their derivatives. So this will just be f prime. This will be a product rule, so it's going to be 1 times f plus x times f prime. And then you take the Wronskian, which is these diagonal products. So what I'll get is f times f, which is, we can write as f squared, and f times this thing. I'll write it like that. And then you subtract. Well, this direction you get x, f, f prime. And what happens there is those terms cancel out, so my Wronskian is f squared, and we need it to be greater than 0 or not 0, which in this case we know it's going to be greater than 0, simply because this one is never 0. We know that this one will never be 0, and that's enough. If the Wronskian is non-zero, that implies that this function, these functions, are linearly independent. Okay, number 8, we want to find the solution to this initial value problem. So we start with the characteristic equation, because this is a constant coefficient homogeneous differential equation. The characteristic equation is r squared minus 2r plus 1 equals 0. That will factor as r minus 1 squared equals 0. So this has a repeated solution of 1. So you get 1 twice. And so we know that the general solution then is going to look like this: c1 e to the x plus c2x e to the x. And now I need to find the particular solution, or the actual solution. Specific, I think, is the word I'm looking for. I'm looking for the specific solution that satisfies these initial conditions. Well, I'm going to need the derivatives, so let's get that. This will be c1 e to the x plus, and here I use product rule, c2 e to the x plus c2x e to the x, and then I plug in. So I know that I'm supposed to get e when I plug in a 1. Well, plugging 1 into this is going to be c1 times e to the 1 plus c2 e to the 1. And if you factor out and cancel the e or divide both sides by e, you get this equation, c1 plus c2. And then I'm supposed to get 3e when I plug 1 into the derivative. So I get c1 plus c1e plus c2e. And then when I plug 1 in here, I'm going to get another c2e. So again, I can divide out the e. I get 3 equal c1, and there's going to be 2 c2. So solving that system, I can take and subtract this top equation from the bottom one. So 3 minus 1 is 2, c1 minus c1, that gets rid of the c1, 2c2 minus c2 is c2. So I get c2 equal 2, and then plugging back into this equation, if c2 is 2, then this would have to be minus 1. So c1 equal minus 1. So my solution would be, my specific solution would be minus e to the x plus 2x e to the x. Satisfies the differential equation and the initial conditions.